All right, everyone. I am here with Roberto Bondesan. Roberto is an AI researcher at Qualcomm. Roberto, welcome to the TWiML AI podcast.
Hi, Sam. Thank you.
I'm really looking forward to our chat. We'll be talking about your paper at ICLR, Probabilistic Numeric CNNs. But before we dig into that, I'd love to hear you share a little bit about your background and how you came to work in AI.
Sure. So my background is in physics, and that's how I got into AI, by basically applying deep learning to some physics problems. So before joining Qualcomm, I was working on characterizing new phases of matter and their potential for quantum computation. So phase of matter is basically one of the states in which you can find matter or materials around you. And one classical example is provided by the easy model. So in the easy model, you have some binary units, some bits which can be either up or down, and you can find this system in two phases. One order phase, which is at low temperature, where all these units, we call them spins, point in the same direction, and a high temperature disorder phase where these units point in random directions. It turns out that characterizing phases of materials is a very challenging problem, and so researchers in the field, they started to use AI for that. So that's how I got into AI, and as I was just learning about the techniques that were being developed, this was around 2017, 2019 for these problems, I got very interested in AI per se, and then I decided a career shift and to move indeed to do research in AI. At this point, it was also when the paper by Taco, Cohen, and Max Welling, who are my colleagues at Qualcomm, their paper on spherical CNNs came out. And so at that point, I understood that studying neural networks using insights from physics was a very useful and interesting thing, and that's what I wanted to work on.
So were you familiar with the spherical CNN paper before you came to work with Taco and Max?
Yes, definitely. That's indeed one of the links that brought me to Qualcomm, yeah.
Oh, that's fantastic. So tell us a little bit about your research interests.
Yeah, so after I joined Qualcomm, I got involved into quite a few exciting projects. So one of them has to deal with neural data compression. So here the problem is that you want to compress data to send them over to some receiver, and you can actually use neural networks, in particular some forms of autoencoder, to do that. So that's a quite interesting problem from the theoretical point of view. It involves generative modeling and things like that, but it is also super impactful because it can immediately translate into different ways to compress data. So that's a very interesting direction. Otherwise, I'm also very excited about quantum AI. So after joining Qualcomm, I also had the chance to develop some ideas around quantum deep learning. So this is the intersection between quantum computation and AI, and so here is where also my background in quantum physics was quite useful to get started quickly on this field, which is a rapidly developing field, which I think is one of the most interesting directions which can disrupt AI in the future. And finally, more recently, I got interested in also applying machine learning to combinatorial optimization problems. So, in industry, we have a lot of combinatorial optimization problems to solve. And so the potential of using machine learning to, improve on the classical techniques is very interesting. And again, this is a very interesting, area between, very theoretical mathematical work, which, is interesting to me, and also very impactful work. So yeah, in summary, I had the chance, of both doing impactful work for society, I would say, at large, but also, being able to do some long-term research like quantum AI. So I'm very excited about, a few things that are going on at Qualcomm right now.
Nice. And when you say combinatorial optimization,
Yeah.
these are problems like traveling salesman and map coloring and that kind of thing, like classical combinatorial problems?
Yeah, precisely. So in fact, in the last few years, maybe 3-4 years, there's been a quite good progress on using deep learning for these problems. So traveling salesman indeed is the standard paradigm of a combinatorial optimization problem, right? When you have a salesman, we need to find the optimal tour to visit a series of cities. And so it has, of course, also direct applications in industry, for example, vehicle routing, right, where a company has to deliver stuff, and so it needs to find the optimal route. And so, yeah, traveling salesman is certainly a great example, and it also historically has driven most of the research in combinatorial optimization, and still it is also in the intersection with machine learning. But also, I'm thinking about other problems like chip design, or some problems, combinatorial problems in wireless. So these are also problems that are hard. So in fact, there are some NP complete problems there, and these are also very interesting application areas for us.
So in chip design, that would be things like routing traces on a circuit board or on a chip.
Yeah, so there are indeed a few stages of chip designs, and all of them, in fact, involve different combinatorial optimization problems. Yeah, so as you say, routing, so finding the optimal connections between the different logical gates or memories on a chip canvas, and also you can think about indeed also placing these components on a chip in the optimal way to minimize area and stuff like that. Indeed, this is all very interesting combinatorial problems where AI could disrupt.
And on the wireless side, I'm imagining that's like frequency allocations and things like that, or what are some of the applications there?
So I have in mind, things like some coding problems where you basically have sent some signal over, and then you want to retrieve what was the bit string that was sent, but your signal has been corrupted by a noisy channel, and you want to retrieve that bit string. So that's one example of things that one could do, or some other error correcting problems and things like that. Yeah.
So there's a bit of a relationship between the combinatorics and kind of information theoretical types of problems and ultimately
Absolutely.
compression, which is where you spend a bulk of your time.
Yeah, absolutely. It is also fair to say, indeed, that all of these problems, compression, also other problems that we work on in Qualcomm, like quantization, these are all of combinatorial nature. So these are certainly possible use cases for this nascent field of ML for combinatorial optimization. Yeah,
Nice, nice.
certainly a broad area. Yeah.
So your probabilistic numeric CNNs paper, what's the problem area that you're addressing there?
Sure. So there, the problem area is the application of deep learning to signals that are not necessarily sampled on a grid. Think about in many applications of deep learning, you for example want to model some time series, and this time series have not been sampled uniformly. So that's one possible use case for the models we want to develop in probabilistic numeric CNNs. But more generally, the motivation there is really trying to think about the signals that we want to model in machine learning in their continuous formulation, not in their discrete formulation, which is the natural formulation you observe when you measure something. And so basically, just to unpack a little bit the title, right? So the title starts with the probabilistic numeric. So the inspiration for this work is really this field of probabilistic numeric. So you certainly are familiar with the convolutional neural network, so I do not need to introduce that. But so let me just spend a couple of words on probabilistic numerics, which might not be familiar to everyone. So probabilistic numeric is a recent field in statistics, which tries to, not necessarily recent, but recently I think there's been a quite big developments, and so it tries to quantify the uncertainty that a numerical program has due to the discreteness of the sampling procedure of its input. To make this concrete, let's think about the problem of computing a numerical integral. You know the function that you want to integrate analytically. You can evaluate it everywhere on a continuous range in its domain, but necessarily you need to sample that function on a discrete sample of points, because your memory and time to compute that integral is finite. And so probabilistic numeric tells you a way to derive uncertainty from this sampling procedure. And the way it is done is via Bayesian inference. So in Bayesian inference, one has an agent, a machine learning model, that has a prior. Here, the prior would be over the set of possible functions that you want to integrate. And in technical terms, it is a Gaussian process. So a Gaussian prior on this set of functions. And then upon measuring that function you want to integrate on some points in your domain, you update your prior to a posterior. And this allows you to immediately translate it to some uncertainty on the result of your integral. So now your numerical program will not just return a number, but it will return a probability distribution. And this probability distribution will be picked around some value, and there will be an uncertainty. So that's your discretization error. So we thought that this is quite interesting also for machine learning. And so we indeed start from the same philosophical standpoint. The images that we want to model in machine learning, the time series that we want to model, are in fact continuous signal. And so we necessarily need to discretize them because we want to put them in a computer. And but this procedure will come with some uncertainty, with some errors. And so it is important to quantify those. And so that's basically the motivation behind this work.
So if I could replay that to make sure I'm understanding, with classical numerical programs, like I'm thinking back to Fortran, numerical computing in undergrad, like you've got some function and you want to compute an integral for it, and you do that. There are established algorithms for doing that. What probabilistic layers on top of that is allowing you to look at the function that you're integrating not as a single function, but as a distribution of functions. And what you have then, then your kind of classic quantization error now becomes a probabilistic quantization error.
Yeah, that's a good summary. Thanks. And maybe just to clarify, so here we are really looking at the quantization, right, in the domain of the function. So the values that the function takes are still continuous, and so that's the kind of quantization we are looking at. And so indeed, in our probabilistic numeric CNN, so we start from this idea, and then we develop on top a neural network.
I just want to interrupt to say that when you say the quantization is in the domain of the function, meaning as opposed to the range, which is think about your vertical, your amplitude. Here we're talking about you're taking different points in time that may or may not be, well, are not uniform. And so that's where your quantization is coming in. So you've got a time series, but you're not getting data in every second or millisecond or whatever. It comes irregularly, and you're trying to figure out quantization error based on that irregularity.
That's precisely it. Yeah.
Okay.
Yeah. All right, cool. So, and indeed, maybe just to give you a little more about the paper. So we develop the idea of using probabilistic numeric for deep learning. So the first step in this procedure is that we start indeed from a regular sample time series, for example, or even from an image which has been subsampled in a regular way. And what we do is that we interpolate that. So we interpolate that in a probabilistic way. So exactly like probabilistic numerical programs do. And that gives us a posterior distribution over our input. And what we do then on this posterior distribution is that we apply a neural net. So now this posterior distribution is a distribution over continuous functions. And so the technical contribution that we make in this paper is to devise a neural network on continuous functions. So typically, your CNN will act on vectors, right? So some array of numbers. Here, our probabilistic numeric CNN is defined directly in the continuum. And that turns out to be quite powerful, and also unlocks new models and new mechanisms for learning, which
What
have
does that,
yeah.
what does that exactly mean? I think
Yes.
I'm so used to thinking about the input to a CNN being a vector. I'm not even sure how to
Right.
unpack it being continuous.
Right. So indeed, you're not going to store that function in your computer because by definition, indeed, you're going to need to have an infinite number of points if you want to store all the values. What you're going to store is just some functional form, some code that allows you to evaluate that function, right? And so that's somehow the input to your neural network. And so to be precise indeed about what happens, we still have a neural network which works by interleaving linear and nonlinear layers. But now, and so the nonlinear layer, you can actually morally understand that it's going to be very similar to what you're used to do. At each point of your function, you apply nonlinearity. But now the real, new part of the work is about the linear layer. So we devise actually a new convolutional layer, which is defined in terms of a linear PDE, a partial differential equation. So this partial differential equation is a linear operation on an input function, which is the input somehow to the PDE, namely the value that you have, the initial condition to your differential equation. So what happens is that if you want to impose actually translation equivariance that you have in convolutional layer, this restricts the forms of differential equations that you can put in your neural network. And interestingly, one of the simplest things you can do is to use a kind of generalized diffusion equation. So diffusion, is a process from physics which you can understand. For example, when you have a glass of water, you put some dye into it, and this dye diffuses over time. And so similar here, we have our image, which is encoded, in some function, and that function gets blurred, similar to the diffusion process over time. So that's really what we mean, by the layer on continuous functions. So it is defined formally, and it turns out that for certain choices, indeed, of layers, we can do computations analytically. So we can actually propagate this, functional forms in our code analytically, and so that's pretty cool. And so we can, ultimately, we can devise a practical procedure to start from our input signal, which was this subsampled signal, then interpolate it, then we apply this convolutional layer as PDEs, we interleave with some nonlinearities, and what we get out after some of these layers and perhaps a pooling and so on, we get out a prediction, like we want to classify this time series, for example, or this input image, and so we want to get out a class label, right, as we do usually. But on top of that, we also get out an uncertainty, and actually this uncertainty is also there at the every intermediate layer, and it's really an uncertainty that is related to the fact that the input signal didn't have maybe information in certain regions of space or time. So in this way, we we can characterize indeed what is the error that we make, and more interesting, we can also choose where to sample the signal in order to reduce uncertainty. So these are all interesting applications that we can think about with this model.
Is
So
that latter point, choosing where to sample, is that um, a like a byproduct of going through the process in the same direction, or is it more like going through the process backwards? I don't know if that question makes
yeah,
sense.
it's going to the process backwards. You're right. So somehow you basically find a certain uncertainty, and this
Yeah.
uncertainty will be a function of where you evaluate your inputs. So you can compute some kind of derivative of that with respect to the inputs to minimize the uncertainty, and
Mhm.
that's that can be useful, when it is, for example, costly to get data points. Right, you can optimize
Yeah.
for the points that are most informative, or when you have maybe some data on meshes and things like that, where discretization errors are important. So there are a lot of interesting use cases. So in this paper, actually, we focused mostly on benchmarking this model on a couple of data sets. So one is the superpixel classification of images. So it's superpixel, is just an image which is subsampled, but again, the points are
Mhm.
not on a grid.
Before we get to
Yeah.
the benchmarks, I have another question about the architecture here. So you one of the key innovations or contributions, it sounds like, is this PDE layer,
Yes.
and PDEs arise in physics all the time. Like you can, I'm imagining the inspiration of that was thinking about the problem, like the closed form problem, and how you might solve it, and then that involves PDEs.
Yeah.
Um,
Yeah.
eh,
So PDE. Yeah. Go ahead. Sorry.
no, no, I was gonna, but then you get to that, so that you have this PDE layer that you think needs to be involved in here, but you have the constraints of translation and variance from CNNs, and then suddenly you're like, okay, diffusion is the answer. And like, where did that come from? Was that did you recognize diffusion as like a translational independence by thinking about a glass of water, or is that like a known physics thing?
Yeah.
Or
So the way we got there, and actually, I would like at this point to amend one of the big omissions that I've done in the beginning, which is not to acknowledge that the first author of this paper is Mark Finzi, who was doing an internship with us last summer. So he's really the main driving force in this project. And so, Mark came up with this proposal, and I guess it was a bit of a mixture of two things. One thing was intuition, and the other thing, maybe coming from physical reasoning, and the other thing was also just mathematical formalism. So we wrote down, the most general, basically local, linear layer in the form of the PDE, and then, basically this turned out to be diffusion when you impose translation invariance. And actually, we also, did something a bit more general. So we also considered, symmetries like rotation and things like that. Yeah, so we talked a little bit about spherical CNNs at the beginning. So there is interest in the community in characterizing equivariance under more general symmetries. And so it turns out that, beautifully also in this context, we can get, PDEs which are, equivariant under more general transformations like rotations and things like that. And that's actually quite interesting, I believe, because, one of the problems with, getting to work also the equivariance under rotation, say, is that you necessarily need to discretize things on a lattice. And so at that point, the rotation for a certain angle becomes, pretty tricky to get it to work well, and necessarily, you will have some error, which is due to the basically mesh of your lattice and so on. In this context, we avoided this problem. So our model is defining the continuum, and it is basically equivariant under arbitrary rotations. So that's a pretty cool, I think, feature, and also equivariant on the arbitrary translation. So that's, I think, a pretty cool feature too.
right,
Yeah.
yeah, I'll just interject really quickly that this whole idea of equivariance and spherical CNNs and gauge equivariance is a big focus of the AI research team there at Qualcomm. And for folks that want to dig in more, probably the best place to start is the first interview I did with Max Welling on gauge equivariant CNNs, where we talk about a lot of this, what equivariance is and why it's important. And we'll drop a
Yeah.
link to that in the show notes.
Yeah, thanks. I also listened to that. It was a great episode. Yeah.
Awesome. Awesome. So you were talking about benchmarking.
Yeah, indeed. So I was talking about the fact that we benchmarked on a couple of data sets. So the first one was this superpixel images. So you start from an image, and suppose it is defined on a grid, and then you subsample it. So you take away some of these points in such a way that then it becomes the grid structure is lost. And at this point, your regular CNN will not work well for this data type. There are a few other competitors out there, but it turns out that our model basically established a new state of the art for this task. So 3 times reduction in the test error. And so this was quite encouraging. And we also applied the model to a medical time series. So in this case, you can think about a patient who goes to the hospital, and then for example, the doctor measures blood pressure or things like that, and this is done at irregular times, right? So this is also a good case of a irregular time series. And then based on these measurements, you want to predict if the patient will recover or things like that. And in fact, so these are pretty important data sets to look at. And so we also applied our model to these data sets and show competitive results there too. Yeah, so we basically think that this point of view is very powerful. And yeah, in fact, we have a few future directions in mind that came after this work.
And what are those?
Right. So one of the interesting directions for this work, in my opinion, is to connect it to quantum computation. In fact, one of the promising platform for quantum computation is a so-called quantum optical computer. So here, optical means that you use light as the basically unit of information that you want to manipulate. And it turns out that there are states of light that people know how to build in a lab, which are closely related to Gaussian processes. So there is a beautiful connection here between states of light and Gaussian processes, and immediately this spurs a connection also between our model and a possible generalization to a quantum model, so a quantum neural network. And so I'm excited about this because it seems to me a very natural, basically, way to encode the data via this relationship between Gaussian processes and certain states, Gaussian states of light. So that's, I think, a very natural way to encode data in a quantum computer, which operates with optical elements. And therefore, there is also a nice way to interpret basically the probabilistic numeric neural network from this point of view of quantum information, a quantum optics, a quantum mechanics. So that there is a big, basically, direction here that I'm excited about, which spurred out of this paper actually, and this new way to think about inputs to a neural network, to think about neural networks.
And is the primary connection there thinking about continuous functions, or is there also this aspect of missing or irregularly sampled data?
Yeah, I would say both. So the fact that indeed you have continuous function relates to what physicists call basically kind of model that physicists use, which is called quantum field theory. So the quantum field theory is also a continuous field, and so your continuous field classically, right, which is your function, which is continuous, becomes now a quantum function. So it becomes a quantum field. And this is quite exciting, I think, because these quantum fields are relevant for describing, elementary particles. So this kind of experiments that you see, in these big colliders like CERN and so on. So this, continuous formulation allows you to make a very interesting connection between very different fields, which are described by very similar formalism. And so this is a very interesting thing. And also the sampling, the irregularly sampled nature of the inputs is also, I think, naturally captured in terms of these Gaussian states of light that I was talking about. So yes, I would say both, in my opinion, are very natural candidates, that allow you to, I think, propose interesting models for quantum neural networks.
Mm-hmm. And what are some of the, you talked about kind of the going back to the benchmarks, the subsampled images, and the healthcare time series. Is there also a compression application for this paper as well?
No, I would say that compression was not our main focus, but I can see maybe where you're going. So if you can condense, your input in some mean and covariance of a Gaussian, that's maybe also a way to think about it. You've compressed it to a few numbers. So that's an interesting spin that I didn't think about. So it was not really our focus here, but yeah, might be.
Got it. Cool. So again, this is a paper that you're presenting at ICLR. What else does Qualcomm have going on at the conference?
Sure. So another paper is from my colleagues Tis Rosendahl and Iris Hauben and Taco Cohen. And so this paper is about adaptive neural compression. So here so we talked a little bit before, about what is the idea of neural compression, so neural codecs. And so typically there is a problem, which is the problem that you want to have a small neural network because you want to have a low computational burden to do this codec process. But at the same time, a low complexity neural network will typically not generalize well, right? And so the idea here of the authors in this paper that we present at ICLR was to do adaptive or fine-tuned compression. So the idea is that, okay, you have trained your model on some training data, and now you deploy it. But it turns out that the test data can be different from the training data. As I said, you can suffer from generalization problems. But you can imagine now that in a scenario where, for example, your sender is some at your sender side of the data, you're willing to spend compute time, and you are sending this compressed data to some low power devices like mobile phones. And in this scenario, it makes sense that at your sender time you can fine tune your basically codec on the test data, and then on top of sending the transmitted image or video to your mobile phone, you also send some bits that are related to the difference in the weights of your adaptive neural network codec. And so the authors indeed show that you can indeed reserve some bandwidth for this delta in the weights on top of the bandwidth for the stream of the video that you want to send. And it turns out that if you do that, and if you jointly optimize the model to do the best possible thing, so to minimize the rate, the number of bits that you transmit, and maximize the reconstruction accuracy, you actually can do better if you do this procedure, of sending over some of bits for your updated weights, than if you just occupy the whole bandwidth for your stream. So that's a pretty promising, I think, direction, which can have a few interesting, applications, direct application, impactful, also for Qualcomm.
Guys, I think this one was counterintuitive for me. I may be misremembering the information theory, but I thought like Nyquist or Hemming or something like that said that it doesn't matter how you chop up your channel. If you have a fixed bandwidth, there's some certain maximum throughput that you'll be able to get. But here you're kind of splitting your channel into kind of in-band and out-of-band or something like that and getting better results.
Yeah, so here the idea is really that you want to basically send a certain number of bits, right?
Mm-hmm.
So that's the rate that you're willing to send. So that's somehow the amount of information that you you would like to send. And at that point, you would like to do the best possible job given that constraint. So what is the choice of my codec, of my encoder, right, to give me the best description of my input in such a way that when I decode it, I get the highest reconstruction quality. And so that's the setup. And so in this setup, what we showed is that you can actually reserve some of these bits that you transmit for the weights. And so that was a new idea that people have not thought about. And yeah, in this setting, this is beneficial. But you're right, there are certainly some theoretic bounds to the rate distortion performance that you can achieve, but we are certainly within these bounds. Yeah.
Okay, so yeah, we're talking about the thing that I was thinking about. It applies to the theoretical bounds, but
Yes, I
we're
would
not
say
there
so.
yet. So we have
Yeah,
some ability to operate within that envelope.
yeah.
Makes
I would
sense.
say getting closer to the bound with this procedure than without.
Got it. Got it. Cool. Any other papers, Qualcomm AI research papers at ICLR?
Yeah, certainly. There are a few other papers. I can highlight a paper by my colleague Pim Dehan, who is a PhD student of Max, and he has a paper on Mesh CNN. So here the idea is that you have tasks on meshes like shape segmentation or 3D shape reconstruction and things like that. And so you would like to use a graph neural network for these tasks, but graph neural networks suffer from the problem that they are oblivious to geometry. So by definition of the graph structure, they do not have information about the geometry. So in particular, if you have a vertex with two edges connected to it, it doesn't matter if you move these edges around, basically, because the graph neural networks convolutional neural networks do not see the angle between these edges. And so the idea of this mesh CNN is to use gauge equivariance tools to build this geometry into graph neural networks. And it turns out that if you do that, you get much better results for these tasks on meshes.
Okay.
Yeah. So we have also other works on temporal localization of actions. And also we have we are organizing together with UC Irvine and Disney Research. We are organizing a workshop at ICLR, workshop on neural compression. So that's certainly an exciting opportunity to get together with the experts in information theory, communication, and deep learning to indeed further advance this effort of getting better codecs using neural networks.
Nice. Nice. So you've talked, we spoke earlier on kind of where you saw the probabilistic numeric research going kind of more broadly when you think about your research area and the area of your team. What are you most excited about? Where do you see that going?
Yeah, so indeed we spoke earlier, and I was hinting at quantum neural networks. So this is
Yep.
certainly something that I believe will be a drive for innovation in AI in the future. Recent years, last couple of years, have seen a tremendous excitement in the quantum computing community, with the supremacy experiments. So we are really at an era where we are starting, to seriously think about, these things. And so it's really timely, I think, to get serious about, thinking about how can you use quantum information, quantum computation to enhance machine learning. So that's, I think, a very exciting place to be. It is true that it is still a recent field, and there's certainly a lot to do, and it is still an open question to figure out what's the best way to use quantum computers for machine learning. So that's why I think it's a very exciting area. So I've been thinking indeed a little bit about this over the last year. And so one of the things also I've been thinking about was the problem of benchmarking these models. So we talked a little bit about this direction where you can use the quantum optical computers and the relation to probabilistic numeric CNN and so on. But in general, the problem here is that we do not have these devices to run the quantum neural networks at scales that we would like right now, right? So what do we do? Certainly, we can indeed, based on intuition and small experiments, figure out what are the most promising models. And I think that I worked on was to also try to find an interpolation between your classical neural net and a quantum neural net. So basically, we came up with this quantum deformed neural networks, which is some work I did also with Maxwell. And so the idea here is that you can think about your classical neural network as embedded in a quantum computer. And in fact, the architecture we are thinking about now is the qubit architecture, which is an interesting relation, to binary neural nets, because a qubit is basically the quantum equivalent of a bit. And so there is a relation with quantization of neural network that you can also explore using quantum mechanics and so on. But the most interesting thing is that indeed we managed to map this binary neural nets or probabilistic binary neural nets, in fact, on a quantum computer using qubits. And then we started to deform this model, so to introduce gates which use pure quantum effects like entanglement and superposition. And so we do that in a way that we slowly interpolate between a regime which we can simulate classically, which is basically the classical neural net regime, and the regime which is basically intractable classically, which will require a quantum computer. And along the way, there is some intermediate regime where you can still do some classical simulations using some tools from quantum physics, which are called Tensor Networks. And basically, this allows you to start from a good, prior somehow for your model, which is this classical network, deform it by doing these modifications, and then you can, use classical simulations of the quantum model to learn that. So that you can implement it as a differentiable program. And so we show actually some modest gains with respect to, the classical neural net by introducing these quantum gates, and we can actually provide, the first example where you can simulate a quantum model at the scale of, real world data. So that was interesting for us. But yeah, more generally, there are many indeed different directions at the moment also related to optimization problems. So we talked about combinatorial optimization, right? And machine learning, and also, quantum computing is also an exciting area for exploring new algorithms for combinatorial optimization. So yeah, to summarize, indeed, quantum AI, I think, is a very interesting direction. And also, I also think that machine learning for combinatorial optimization is a very interesting direction. So this is also pretty recent. And I believe that here we will see, large-scale adoption of this technique, because it has been shown recently that you can actually enhance your classical solvers for integer linear programs or stuff like that, which people use routinely for solving their problems in the industry. You can actually augment with neural networks these solvers in such a way that the decisions that these solvers make are better informed and basically are faster. And the idea here is that you can adapt basically your solver to the data distribution that you really care to solve. A delivery company will routinely solve the traveling salesman problem in the same city. It will not want to deal with the most arbitrary hard instances of the traveling salesman problem. And this is where machine learning, I think, will really put an edge. So it will allow you, to tailor your optimization algorithm to the instances that you care about, and ultimately this, leads to, better performance for combinatorial optimization solvers, and and also potentially, it allows you to discover new strategies, like using reinforcement learning, as we have seen, in AlphaGo, AlphaFold. So super exciting field, I think.
Awesome. Well, Roberto, thanks so much for sharing a bit about what you're working on and what some of the folks in your team are working on at ICLR. It's been really great chatting with you.
Thank you, Sam. Pleasure for me too.
Thank you.